Thank you, everyone. Moving forward with the Delhi University Kulgeet, which beautifully reflects the legacy, values, and academic spirit of our institution. I request everyone to kindly rise for DU Kulgeet.
Please, ma'am, login. Thank you.
Once again, we welcome you, ma'am.
Support, please.
I now request Professor Ajay Jaiswal sir and Dr. Deepak Gupta sir to also felicitate our patron of the conference, Professor Payal Magu ma'am. A huge round, everyone. I request sir to also felicitate. I request sir to also felicitate Professor Vineet Kansal sir. Welcome sir. I now request Professor Prajesh Roy sir and Dr. Aditya sir to kindly felicitate Professor Abhishek Swarup sir. Welcome you sir. I again request Dr. Deepak Gupta sir and Dr. Aditya sir to felicitate Professor Ajay Jaiswal sir.
Can come actually.
Now, to acknowledge our keynote speakers who are present today, I request Sameer sir to kindly felicitate Dr. Ishwak. Huge round of applause, everyone. It's very important. Welcome, sir. I now request Gurjeet ma'am to kindly felicitate Dr. Kavita Khanna ma'am. Yeah. Now, to felicitate the committee members who've been tirelessly working for the conference, I request Payal ma'am and Vineet Kansal sir to kindly felicitate all the committee members and organizing team. I invite Professor Prajesh Roy sir. I request Payal ma'am and Vineet sir to felicitate Prajesh sir. We'll also invite Professor Pramod sir. Professor Pramod sir. Next, I'll invite Mr. Dikshant Awasthi sir. Professor Samir Anand sir. Gurjeet ma'am. Huge round of applause, everyone. Come on. Everyone got behind. Dr. Gulshan Srivastav sir. Sir. Dr. Aditya sir. Once again, thank you everyone for your valuable contribution.
At last, I have Nupur ma'am.
Once again, congratulations everyone. Now, before we start with the conference, let me share briefly the remarkable scale and vision of the conference, already shared by Deepak sir, but just to highlight it again. DOSCI 2026 and Comsia 2026 aims to bring together brilliant minds, scientists, academicians, researchers, students, and industry experts from across the globe. The goal is simple yet powerful: to exchange ideas, inspire innovation, and transform research into real world application. This year has truly been exceptional. Receiving DOSCI has received 1020 papers in participation from across 13 countries, and Comsia received around 1900 papers with 20 papers accepted across 19 countries. And that is not all. The Ideathon saw an overwhelming response of over 1540 teams, with only 15 finalists making it to the final stage. A big round of applause for everyone for this incredible participation. And a sincere gratitude to Stringer and Zyber SSRN for their support and research guidance. Now, moving further, I request our esteemed dignitaries to kindly join us for the official launch of the conference proceeding of Comsia and DOSCI 2026. Once again, congratulations to all the students, researchers, scholars, who participated in this proceeding. Huge round of applause.
Yes, yes, please.
Moving forward with the address segment, I first invite Dr. Abhishek Swarup sir to share his thoughts about this one.
Thank you. Good morning, esteemed guests, respected speakers, and the dear participants. It is my great honor and privilege to welcome you all to Doctoral 2026 and Comsia 2026. On behalf of the organizing committee, I extend a warm greeting to everyone present here today. This conference brings together great minds, innovators, researchers, and professionals from diverse fields, all united by shared passion and discovery, collaboration, and progress. DOSCI 2026 is just not an event, it is a platform where ideas meet opportunity, where knowledge is exchanged, and where the future begins to take shape. Over the course of this conference, we will engage in insightful discussions, thoughtful, thought-provoking presentations, and meaningful networking. I encourage each one of you to actively participate, ask questions, share your perspectives, and take the most of this opportunity to learn and connect. I would like to take a moment to express my sincere gratitude to our keynote speakers, sponsors, partners, and the entire organizing team, whose dedication and hard work have made this event possible. As we begin this exciting journey together, let us remain open to new ideas, embrace collaboration, and strive to create impactful outcomes that extend beyond these conference halls. Once again, I welcome you all to DOSCI 2026 and wish you a highly productive and inspiring conference. Thank you.
Thank you, sir. I now invite Professor Vineet Kansal, sir, to address the gathering.
Welcome all of you. I can see a lot of young faces here and a lot of students. I don't know how many are, are the contributor from the field, but it's good to be the participants of the conference and such events. I'm associated with this Doxy, this is sixth year in continuation, and though it is a seventh one, I was not there in the first one. I could see there are a lot of meaning and contribution in terms of the quality. The Doxy itself is talking about you have 1,000 plus contributions, and there are some 15% to 18% submissions acceptance, and that varied to from last 13 countries. So it speaks about the quality of it. But the people who are here joined physically and present in this hall, and the students or the participants or the faculty colleagues who are online, I would like to have a few things to share. First, we are talking about the computational intelligence, and there has been a hype of many things which we are talking about. And if we see honestly, in last 30, 40 years, when we were graduating our engineering programs, we were studying these courses, artificial intelligence, and etc. Computational powers in terms of
impactful in terms of touching the lives of common man, whether maybe the field of agriculture, pharmacy, advanced research in many fields. Once and until you do not touch the common man and you do not have the global vision, you can't achieve much larger goal. That is how I see it. And many people, many associations do a lot of networking, a lot of commitments. But how much comes to the ground reality, that we need to see, what is going on last 2 to 3 weeks globally and internationally. So we have to come out to our natural intelligence, as I always say, and an artificial intelligence or computational intelligence could be a supporting and assistive tool. If it takes too much of it and you go too much of clinically, and do not look forward, and do not believe your own instinct, the global health is not going to improve. And the message to the youngsters who are joining this work, take away the practice. Until you do not ask questions, do not engage yourself, you do not learn. Every occasion like this should be taken as an opportunity of learning. Apart from the classroom settings where you go, teacher speech and you write an exam assessment, there is no assessment. But life is going to assess you based on all those occasions, the opportunity you have it. So my request and advice to all industries would be engaged, be interactive, learn out of it, make a compendium, out of this, and make a, things how progressively things are moving. So it will be good, and I congratulate, entire team, and look forward all the best for this conference. Thank you very much.
Thank you so much, sir. We also have with us Professor Girish Chandra, sir, who's there with us in online mode. I request sir to kindly share a few words.
Okay, so the chief guest, am I audible? No? Chief guest of the occasion, Professor Anu G. Agarwal, Professor J.P. Pandit, Chief Patron of the Symposium and our Vice Chancellor Executive, the esteemed patrons, Professor Vineet Kanshal, Professor Payal Mago, Honorary Chairs, Professor Oscar Castillo, Professor S.K. Mishra, Professor Hasnian, Symposium Chairs, Professor Abhishek Swarup, Professor Ajay Jaiswal, Professor R.K. Agarwal, and Professor Balas. Editorial chairs, technical program chairs, keynote speakers, our conveners, faculty colleagues, and the doctoral scholars. A very good morning to all of you. It is a distinct pleasure to welcome you to the inaugural ceremony of the Doctoral Symposium on Computational Intelligence, Dosci 2026. We are gathered here at the historical inflection point. The transition we are witnessing in computer science today is not merely incremental. It is a fundamental re-architecturing of how machines interact with the world. We find ourselves at a crossroads where the theoretical boundaries of computer science are being redrawn. The research presented here over the coming days is essential groundwork for a society increasingly defined by autonomous intelligence. For decades, our understanding of efficient versus hard problems has been anchored in classical complexity classes. However, we must now acknowledge a fundamental shift. The advent of quantum computing has shaped a total revolution of our complexity framework. Algorithm once deemed hard, just a minute. The algorithm once deemed hard or computationally secure are being re-examined through the lens of quantum vulnerability. As researchers, we possibly need to move beyond the traditional P versus NP paradigm and begin designing for a post-quantum world. This is not just a hardware shift, it is a mathematical one. As scholars, your task is to redefine security and optimization for a post-quantum era, ensuring that our digital foundation, especially in cryptography, remain resilient when the impossible becomes executable. A profound shift in the domain is evolution from generative AI to agentic AI. We have moved past the era of the chatbot that merely predicts the next token in a sentence. We are entering the era of AI agents, systems characterized by autonomous reasoning, multi-step planning, and recursive tool use to achieve high-level goals. Unlike standard models that wait for a prompt, an agent can perceive an environment, reason through a complex chain of thought, and execute actions independently. This introduces a new research frontier, agentic alignment. How do we ensure that an autonomous system's goals do not drift away from the user's original intent? As these agents begin to handle financial transactions or scientific discovery, the math behind their decision making must be as robust as the code that powers them. As we push boundaries of the model capability, we encounter the critical challenge of explainability. In theoretical research, a black box model might be acceptable. However, in safety-critical systems, it is a profound risk. In fintech and banking, an opaque algorithm can inadvertently break in systematic bias or trigger flash crashes. In aerospace and defense, from autonomous navigation to rocket launch sequences, trust cannot be a leap of faith. It must be verifiable. So we need traceable reasoning, where every decision path is mapped into justifiable and mapped and justifiable. We need systems that can explain why a certain trajectory was chosen or why a credit risk was flagged. Uh, Finally, we must also address the material science of the field, which is the data infrastructure. In many sectors like banking and healthcare, AI scale is currently constrained not by model intelligence, but by data readiness. We sit on the oceans of data, yet it remains fragmented in incompatible silos or locked behind rigid, antiquated governance. To move from fragmented to trusted, we must build public data infrastructure that enables interoperability standards, ensuring data flows securely without losing its semantic integrity across fragmented silos, and consent-driven ecosystem that builds frameworks where privacy and governance are baked into the data layer. And moreover, the trusted environment moving toward scalable, responsible data systems that enable innovation while protecting the public trust. The questions that are left to the researchers as food for thought is sustainable AI. Can we achieve high fidelity reasoning on edge devices with a minimal carbon footprint? And agentic reasoning can be moved from AI that predicts to the AI that plans through complex multi-step scientific problems. And moreover, the ethics of autonomy. How do we maintain human agency and intuition as machines take over high-stake decision making? The history of AI began with the dream of machines that could think. Today, the dream is a reality, but its responsibility stewardship lies in your hand. As researchers, you are the architects of this new reality. I urge you to use this symposium to challenge the black box, to question the limits of classical complexity, and to design agents that are as skilled as they are efficient. I want to thank our international collaborators, our dedicated organizing team, and our sponsor for fostering this environment of innovation. I wish every participant a fruitful, intellectually rigorous, and inspiring experience at Dosci 2026. Thank you.
Share was reading there.
A very good morning to all of you. We have with us Professor Anu Agarwal as our chief guest for today's conference from Department of Operational Research, University of Delhi. On behalf of School of Open Learning and organizers of the conference, I heartily welcome you, ma'am. We have with us Professor Abhishek Swaroop, Professor Girish Chandra, who was just online with us, Professor Vineet Kansal, and Professor Anjay Jaiswal, Dr. Deepak Gupta, who is convener of the conference. We also have Professor Sameer, Professor Ishwak, and Dr. Kavita Khanna as our keynote address speakers. And all delegates, once again, on behalf of School of Open Learning and Shahid Rajguru College, as well as all organizers of the conference, I heartily welcome you to International Symposium on Computing and Communication System for Industry Application, Comsia, and 7th Doctoral Symposium on Computational Intelligence. Computer vision, if we say, is an innovative technology which has made significant advances in recent years, allowing computers to understand and analyze visual information in a way that is comparable to human perception. And the field of computer vision is seeing rapid growth, leading to numerous advancements and creating opportunities for diverse applications across several industries. With artificial intelligence gaining momentum, the field of computational intelligence and advancing computer technology all will gain greater significance, and conference and symposia like these will help young learners stay updated with these trends. To further take up this vision, this year, a seventh doctoral symposium on computational intelligence, DOSCI 26, is being jointly organized by School of Open Learning, University of Delhi, Shahid Doctoral College of Applied Sciences, Government University of Delhi, and Institute of Engineering and Technology, a constituent institute of Dr. APJ Abdul Kalam Technical University, Lucknow, in association with University of Calabria, Italy. The goal of this seventh doctoral symposium on computational intelligence is to provide a shared forum for cutting-edge scientists, academic research scholars, students, and industry professionals working in the field of computational intelligence. And as in the starting only, Mr. Deepak Gupta said that he has received so many papers this year and showed a short video also where a comparative growth of this conference was also very much remarkable. And today we will have several sessions as well as several keynote addresses, and these sessions will definitely lead us to learn the recent advances in artificial intelligence and machine learning, intelligence network, techniques and application, smart technologies, utilizing artificial intelligence, Internet of Things, blockchain, recent advancements, innovations, intelligence, and Internet of Things, as well as emerging technologies and their impact, and so much more I think you are going to get. And definitely this will be a driving force for innovation and technology advancements, and we all as participants will learn a lot and will probably be able to provide certain policy inputs also after the outcome of this conference. And I, on behalf of all the organizers, I heartily say thanks to all of you, heartily welcome you, and may this conference will be very useful for our future technology as we are moving into the field of artificial intelligence. And this conference, I think, will be a landmark, will be a milestone in the future progress of innovative technologies like artificial intelligence. Thank you so much, and once again, I welcome all the participants.
Ma'am, moving further, the moment everyone has been waiting for, I request our esteemed chief guest, Professor Anu Agarwal, ma'am, to address the gathering with her words.
Sessions, Professor Tal Mohammed, President from Dr. Quality, the organizers of the conference, Principal Professor Ajay Jaiswal, Professor Sanjay, Dr. Very warm, and all the delegates and the students. First, a very good morning to all of you. It's a really a privilege and honor to be part of this solemn ceremony and part of the inaugural session. It's an honor for me. Thank you to the entire organizing team. Today, when we talk about this conference, today we are doing the use of technology, their artificial intelligence, machine learning, cloud, they are transforming our lives. They're just not impacting us in a big way, but they are changing. They are changing the way we live. They are changing the way the businesses are being run. They are embedded. The technologies are embedded everywhere. If you take the example of the smartphones, they have become like, I'll say, they have just become like a Aladdin's Chirag in our hands.
They think of a wish, they want to make a wish, they want to buy something at any odd hours. The smartphones, they are like, they are the answers. You think of anything at the convenience of the time, convenience of place, you can shop, you can buy, you can browse, you can learn. The opportunities are just boundless. If we talk about, with the emergence of this natural language processing tools, with the enabling of how the text can be converted to audio, videos can be summarized to the text, or even the text can be converted to audio. Even the physical inabilities they have, no, it's not, they are not the barriers to learn. So, if we are willing to learn, then geographical boundaries, any deficiencies, there are no barriers. Any person living in the faraway cities need not come to the town to learn from the universities. The universities are at their fingertips. The knowledge is in their phones. Through YouTube channels or the education has become, I would say, it's affordable. Technology has made the learning experience more inclusive. Farmers are using chatbots. I just want to share, one experience. Like when I go to my balcony in the morning and I see some plants instantly, what I do, I'm not from the bottom background. What I do, I just take a photograph, I use the app, and just see what is wrong with the plant. And the solution is in hand. That is the technology, that is how to start moving us. Before I go to the class, if I feel, as a teacher, many times, even we find difficult to understand something. I go to any generating energy, ask questions, get answers. Verify, definitely I verify from the books as well, I verify from the secondary sources as well. But things, how we learn, how we teach, how we perform, that has totally, transformed. Like Professor Kendall was saying about the time when we were the students. I remember the time when I was a student and I was in class 12. And that was the time in my school the computer. And nobody in the school was not allowed to touch it. We were just, it was like a something unique. The black screen and with the cursor blinking. And there was so much, fascination about that machine, the keyboard, and we were so much fascinated that how that, like we in our childhood we spent our initial primary school learning the tables. In the class, we used to spend time and that machine was capable of all the calculation within fraction of seconds. That was a miracle for us. We belong to an era, where if you miss a class, then next day we were like after our classmates to please give us a notebook so that we can copy our notes so that we can catch up with what has happened in the class. Nowadays these are not the barriers. There is a WhatsApp, students share the notes. We teach in the class, we see photographs and then entire notes are given in the class. So that is how the technology is just transforming everything. Now what the businesses are doing. Okay. They are using the technology to offer customized services. They learn what we browse. I remember the day I just was, on Amazon, I just was watching, I was just browsing for handbags. And I just didn't buy. I just browsed it and I just forgot about it. But what happened afterwards? Whenever I went online, that handbag was always flashing in front of my screen. That am I still interested to buy it? So that is, how the technology is transforming the businesses. They are using it to sell. They are using it to cross-sell. Cross-sell means if you're buying, if you're booking a air ticket, the offer will be to book a hotel. They are using it to upsell. Means they will show you if you're interested in this book, you may be interested in this book as well. They are, doing it, to resell. They will show what you have bought. So that is, how the technologies in they are like. And farmers, farmers are using chatbots for better utilization of for the irrigation of drone technology. So it's it's just like we'll say that, the things, which were just unimaginable even 5 years before, they are just possible now. So I don't, even I think, we don't know how the technology is going to affect us in the next 5 years. But yes, when we talk about the conference on the themes like intelligent systems, computing systems, yes, the seeds of tomorrow definitely are sown in the conference like this. I mean, there is a history, like we know how the internet came to be. It was just a small group of students working together how to integrate their computer system. At the time, they never knew that this technology, what they started in the room, how they're going to transform lives, billions of lives worldwide at the global level later on. Now we can be imagine our life without internet. If you forget the phone, I remember, I know it, I do it. Like if I remember my phone while coming to my office, I go back. I miss the university class, but I'll go back and get my phone first. Because I cannot imagine, myself a day without a phone. And I think that is true for all, maybe all the young generation. When I, drive out of my house every day, I know the roads. Every day when I come to the university, I open the navigation app. I know the roads. I have been traveling for last 25 years, but still I open the navigation apps. Why? Because I know the roads, but I don't know the traffic conditions. So I want to take the route which will, take me the fastest possible. So that is the power, like how much dependent we are on the technology. And, so, but what technology lies ahead, that will emerge definitely from this conference. I suggest all the young researchers, all the students here, that please never accept the assumptions. Never accept the set norms, challenge them. Ask the questions. If a teacher says this is how it is done, raise the questions. Challenge the assumptions. Question the norms. Because when we think beyond the system, present system, only then the new things happen, the innovation happen. So with this, I would like to end here and wish all big, the conference a big success. And I definitely sure all the students, all the researchers who are joining this conference, they have a lot of food to to carry home. Get a lot of ideas to carry on with the research and to carry forward what we are here forward. One thing which I definitely would like to mention here nowadays when we talk about artificial intelligence, people many times there's a debate: is it acceptable human intelligence? Will it going to overtake the human intelligence? But if you see the history, whenever any technological advancement has taken place, whenever any development has taken place, always there has been approach. Had we not accepted, had we not, uh, followed the path of technology, then we would have, as a human being, would have still been living in the Stone Age. The journey from Stone Age to the, already in the jungle or on the trees, to the lights, what we are living in the skyscrapers, that journey has been possible because we have accepted the changes. So when we are talking about when there's so much noise that is AI affected intelligence? No, it's not affected. But yes, there is a need to create home working spaces. We need to integrate the human networks with AI. We need to create co-intelligence systems where human beings and AI tools are working together to create better solutions to make our society more inclusive, for the betterment of the society. With these words, I thank you.
Now, for highlighting the importance of such events to understand technology better. Now, to conclude this inaugural session, I invite Mr. Rajat Jaiswal, sir, to present the formal vote.
Honorable Chief Guest, Professor Anurag, Honorable Conference Patrons, Professor Payal Marco, Director Campus of Open Learning, University of Delhi, Professor Vineet Kansal, Director IIT Lucknow, Professor Abhishek Saru, Dr. Deepak Gupta, keynote speakers, my dear colleagues, and dear participants. A very good morning to one and all, and greetings to all those who have joined online. On the behalf of organizing committee of Dosci and Comsia, it is my privilege to propose both of things on this occasion. First and foremost, our deepest gratitude goes to Chief Guest Professor Anurag. Ma'am, your insightful address has set a profound tone for this event. We are truly grateful for your time and wisdom you shared today. We extend our heartfelt thanks to our patrons, Professor Payal Marku and Professor Vineet Kansal. This conference would not have been possible without your unwavering support, guidance, and the resources provided to turn this vision into reality. We are deeply grateful to keynote speakers, Professor Kavita Khanna, Dr. Muhammad Isha, for kindly agreeing to share their expertise with our participants. I am sure that all delegates will be benefited by your knowledge and expertise as they move forward in their own professional journeys. Sincere thanks to all session chairs and judges to National Ideathon. I also thanks to all the delegates for their participation in this conference. Finally, a big thank you to organizing team, Professor Abhishek Saru, Dr. Deepak Gupta, Professor Pajesh Roy, Professor Pramod Kumar, Professor Sameer Anand, Dr. Abhishek Tandon, Dr. Gurjeet Kaur, Mr. Dikshant Avasti, Dr. Deepak Sharma, Dr. Mukul Gosai, Dr. Gulshan Srivastava, Dr. Aditya Kamparia, Dr. Upen, and Dr. Reema Thareja, Ms. Asha Yadav, Ms. Aishwarya, Dr. Charu, and Ms. Varsha. I also take opportunity to thank Dr. O.P. Sharma, Deputy Registrar, for his valuable support in organizing this conference. I also extend sincere thanks to all the technical staff and all the volunteers who worked for the success of this conference. Thank you all once again for your presence and contribution.
Thank you, sir. With this, you officially commence the conference open. I request everyone to kindly join for high tea, post which our session will continue.
A very good morning, good afternoon, and good evening to all the participants out here. And firstly, I would like to thank for making me a part of this conference. And I can see the quality of the people that have been here at the quality of the conference in its inception. So I would like to congratulate the organizers for maintaining such a quality of the conference. The talk I'm talking about today is the journey to building large companies. You must have been familiar with the topic. So let us start. As our chief guest started, but with the thought that yesterday is a history, tomorrow is a mystery, today is a gift, and that's why it's called present. Yes, we all have witnessed the history of the things. You are from a young generation, but as our chief guest also we have not seen, we were there and we had not seen the technology in our initial days, and we seen the evolution of technology since then. So if I remember the time when I firstly came to Delhi, we used to travel with a book of maps. I was totally unaware about the roads and the other paths, and I used to carry with a book of maps and used to navigate the roads through that. And not only days when I was doing my PhD, I remember that to have one journal paper, which our supervisor used to tell, we used to study, you used to spend so many hours in the library to find out one good paper in that area. And now, your generation, I think the young generation that comes in, it's really, really blessed to have the facilities, the technology that comes for you at every step and helps you at every step. Even if like I feel that when I was a student, I come from a very small, humble background, and I used to feel how it would be like when the professors teach at Stanford or MIT. But now when I see that wherever we are, we can listen to the lectures from the professors from Stanford or MIT. If you are from computer science, like I feel that when I was studying computer science, I was studying the course analysis and design of algorithms and used to study the book Foreman. So, I mean, it was so good to see the lectures of Foreman on MIT OCW when it came into picture. And now when you can see, you can study the latest technologies from the best of the resources that are around. So that's the reason that, yesterday is a history, tomorrow is a mystery. We really do not know what is going to unfold in the future. And today is really a gift. We need to really enjoy and make the best out of the time that we have and the resources that the technology has given to us. When we talk about the major highlights of 2023, not long time back, you must have seen that GPT passed the bar exam. GPT has outperformed, so many things in maybe SAT exam or maybe GLAT exam or major examinations, and GPT has passed and surpassed the human performance as well. So if you see the statistics time, it took GPT to reach 100 million users. If you talk about Twitter, it took 5 years, 2 months to reach 100 million users. Facebook took 4 years, 7 months. WhatsApp, our lifeline for every day nowadays. It took 3 years, 4 months to reach 100 million users. Instagram, I think I always tell, even to my daughter that, and to the younger generation, that they live on Instagram more and less on the earth. So their favorite place is Instagram. And this favorite application for today's generation, it took 2 years, 4 months to reach 100 million users. And ChatGPT, it just took 2 months to reach 100 million users. So that's the power, that's the technological power that it has brought to all of us. But the thing is that ChatGPT is not new. I talk about the precedents. You talk about, you must have seen Google Translate, you must have seen Siri, Alexa, you must have seen the completion of the emails while you were typing on your Gmail. So all these, all these things, they use certain things which are a building block for what we call the generative AI today. And this is the word of artificial intelligence. I think you all must be knowing we have supervised learning, unsupervised learning, reinforcement learning, generative AI. So all these are the building blocks and we have evolved over time. I hope you know what is a supervised learning, wherein you have in your data set, you have the labeled data, suppose you have an email, and you know whether you have the data set in which it is labeled data, that whether that email is a spam or not. Or let's train your model on that data. You can find out or you can apply it on the untrained data. Now, what is language modeling? If I talk about language modeling, so given a sequence of words so far, whatever we say, you predict what comes next. What would be the most likely answer? That is what is language modeling is. So if I say the color of the sky is, and the most predictive answer is blue. But if there is a context before it, that today is a rainy day, the color of the sky is, then the next word would be different. So that is what is called language modeling. Based on the context of what you speak, what would be the predictive response of the model? That is what is language modeling. Tips of creating your language model. First is obviously you have to collect a very large corpus of data. You need to have large data to train your model. So maybe the entire data of Wikipedia, books, stats, Quora, all the social media, GitHub platform, Reddit. So you talk about it, whatever data is available, that is being taken, and with that data, basically, you train your model. And then the second step would be ask the learning model to predict the next word in a sentence. So once you train your model, it is trained on the in such a large corpus of data that it would, do its internal calculations and would try to predict the next word. And this is, being repeated over the whole corpus of the data. That is how the entire, language model scenario works. So if we trace back to the initial things, we are here at this 2026 and we see the technologies, spanning at every application, every platform. But if we start the genesis of it, the genesis of it comes from the artificial neural network. So if we talk about a single neuron, there's a initially the research started with a single neuron. If I talk about a single neuron, what it can do is the capability of a single neuron is that it can do the classification of the data, which is linearly separable. If the data is linearly separable, that means you can separate it into two classes distinctively. If I talk about two-dimensional data, then if you can separate it with a straight line, then that was what was the capability of a single neuron. Then came that we need to increase that capability. We need to enhance that capability. Then came multi-layer perceptron. And in multi-layer perceptron, what happens is that we take multiple neurons, we take multiple layers, and we enhance the capabilities. So with multiple neurons coming in, the capability of the network enhances. And if I talk about this simple, very small network, wherein you see in first layer I have 5 neurons, in the second layer I have, I think, 8 neurons, in the third layer I have 4, and in the final is the output layer. So in this network would perform very limited capabilities. And in this network, if I see the parameters is something which I need to train in the model. Parameters is like something in our brain when we are doing something since the childhood. Something in our minds changes when we learn. That thing comes into artificial neural network in the form of parameters. That when we train the network, the parameters gets learned and parameters they get updated. And when we say that my model is completely trained, I have frozen the parameters. So in this small network, if you see, there are 99 parameters. How come there are 99 parameters? You have multiple weights from one layer to the other. If I talk about the first layer, I had 5 neurons. Second layer, I had 8 neurons. So first is 5 into 8 plus 8. 8 is the bias term that we add. And that is how you calculate the total number of parameters. So in this small network, you see that there are 99 parameters. Now when we move to GPT, if I talk about GPT-4, it has 1 trillion parameters. So you can very well imagine the complexity of the things or whatever happens inside. It has 1 trillion parameters. But the other side is if we talk about human brain, it has 100 trillion parameters. So that is the complexity of the machine. But again, we are human beings, and it's always said that human beings can create thousands of machines, but thousands of machines cannot create a single human being. And that is the power a human mind has. And that is why the human beings have been able to come up to something as interesting as ChatGPT. So if I talk about GPT-4, I told that it has 1 billion parameters, and these parameters have, you can see that they are increasing over the entire landscape of all GPT versions that have come in. But when what happens as we increase the parameters? As we increase the parameters, the functionality increases. Increasing the parameters means we want to enhance the translation of things, we want to do the language summarization, we want to understand the images, or we want to do multiple works on multiple modes. Parameters. Stuff called Llama and all the models that are coming in, they have 480 now, they have 480 billion parameters. if we are developing such models with the increase in the parameters, what is happening is we are increasing the functionality of the model. Now, with so much coming in, what has been the cost? If I talk about GPT-4, it costed $100 million. And how come? It was all the whatever I told you that needs training, it needs multiple resources. So overall, the cost that has come with GPT-4 is $100 million. Now, in 2010 to 2020, if you talk about, there has been a era of, artificial neural networks or deep learning, and then moving on to these large scale supervised learning. As you see in this graph, as the amount of data increases, a small AI model does what? The performance doesn't increase afterwards. So, but we want that with the increase in the data, the performance should increase. And that was achieved with large AI models. With small AI models, the performance was saturating as we were, increasing the amount of data. But in case of, various GPT models or transformer models, as the data was increasing, initial thing was that as you increase the parameters and you increase the data, your functionality increases. As you increase the data, your performance of the model tends to be better. So this is a very, very wonderful visualization tool. I recommend all the students who are here or the young researchers who want to start with the journey of neural network. You can really, you should really explore this to understand how it works. Let me share it. It's a TensorFlow playground. Is it visible?
Secondly, thanks. Just
Let me just connect this so that I can give a good demo of a very good tool.
practice closer or a video with yes. You should look at it. This. So this is sharp also. Because of it. Cross the
So, okay, this is a wonderful tool named as TensorFlow Playground. So, it acts as a basically playground, a visual tool for understanding of the artificial neural network. So, I can, customize it. So, what I said that if I have one neuron, one hidden layer, and I have per se one neuron, and I select the data set per se this, I told you what would happen, that it can only give me a straight line. It would never be able to classify something which is not linearly separable. As you can see, this data set is not linearly separable. But if that's it, and I choose this, and I now run it, and you see that I tend to get a straight line which is separating it. But if I choose a data set or this data set which is not linearly separable, I will run it for 1000 epochs, 10,000 epochs, or I will run it for lakh epochs. It would never converge. The model is never going to converge. So that is the essence. And if you for this model, if I increase the number of layers in each layer, if I add the neurons, if I add the neurons in each layer, Suppose I do this, and now I run it, and you see that the model converges, and it gives me a wonderful boundary for separating the data. So you can play around with this. That's what is named as TensorFlow playground for understanding of the basic concepts. So it has other things also which I'll not touch upon it as of now. It talks about activation function. It talks about the regularization term. So you can play with, if I take this activation function in the layer, what would happen if I take ReLU activation function or sigmoid activation function, what would happen? So you can see visually all these aspects here in this wonderful tool called TensorFlow Playground. So moving back to my presentation.
Presentation was easy.
Okay. Can please help you open the presentation? There is a sorry for this interruption. I'm trying to open my presentation once again. Visualize the simple neural network and what all trade-offs we have when we use a single neuron or we have multiple planes. Now that was a simple multi-layer
Section chair with
perception.
section.
And what is the
मेरे को नाम बोलना तो इसी वो साथ है को
data? It works. But if we want to move on to
डॉक्टर
yeah,
सर्च करनी
says my input. Then the network that we prefer using is a convolution neural network. And in a convolution neural network, the basic idea is that you have convolution layer and you have basically pooling layers that facilitate in extracting the features without increasing the complexity of the model and using the same set of filters. So basically in a convolution layer, what we do is we take
क्या हो रहा है
in a convolution layer we have multiple filters. And what we do is we have multiple filters and what we if I talk about image processing, what happens is that you apply a filter extracts the features. And what here we do is we treat those filters as features. I'm not defining in convolution neural network what filter I take. I learn those filters on its own. So in each convolution layer, I have certain set of filters, and filters would do what? Extract features. So first layer would be for extracting features. So if I talk about any, suppose any dog and cat classification problem, there are certain images of dogs and cats, and I want to take the data. So my first what would extract the primitive features. The primitive features are like edges, vertical edges, horizontal edges. So they'll extract the primitive features. The next convolution layer would do what? Build on that layer and extract the higher order features. If I have the primitive features extracted in the edges, in the next layer I will extracting the higher order features for say eyes, nose, and then in the next layer I will be extracting
21 में भी 21 आज छोड़ना था
for say whatever I want to the application I'm working on. So in a convolution neural network, this is a very wonderful tool that you can use in, that is deep lizard convolution demo to understand how a convolution network works. So let me see if we can open this in video.
आप 5
Can you help me to open this?
ये पीपीटी को क्या हो रहा है तू वहीं खड़ा हो जा मैं कर लूंगा उसे
It's again a plug and play tool wherein so I'm just trying to open a wonderful tool for you, which is Deep Lizard, and it basically gives a very good understanding of the convolution neural network and convolution layers. So if you see here, this is an image that comes up, and as you see, every image is comprises of a certain set of pixels. And if this comes from MNIST dataset, and this is a 0 that comes in. If I apply this filter over this image, what is the output that I get? And if I, move it next step, I'll go next. Likewise, I can see what is the output that comes out when I apply this simple filter to this image. And if I say per se play, it is going to show me magically what would be the output when I rotate or convolve basically this filter onto this image. So that is how, that is the power of a single filter. And you can very well imagine that if I have a layer of filters like this, every filter would be extracting certain set of features for me. And, this filter again, I say that this filter is not fixed. That is the power of any artificial neural network, that we train these parameters. So we do the training, back propagation learning algorithms are there. We apply gradient descent and we train all the weights that we have in this filter. So that is how, convolution neural networks work. So that was just a small demo for a convolution that really helps students understand this aspect. Let me open the presentation once again. So I talked about the convolution neural network. Now I talk about, this was about the images. So if you have an image data, you use convolution. You see any application of images, wherever image is there, self-driving car or whatever. You talk about any image application and a convolution network is behind it. Now comes the, this was the grid type of data wherever we have a grid. So firstly, I talked about the tabular data, then we have an image data or a grid type of data. Now I talk about if I have a sequential data. Sequential data is something like when I'm speaking to you, whatever I'm speaking, every word that comes after has to be understood in that perspective only. So if I say that I gave a session in Dosci, or Dosci gave a session in I, the word, the pattern of the words, the position of the words makes a difference. So we have to read the words the way they are and in the sequence that they are. So when the initial research came in, the first network that was developed was the recurrent neural network. And recurrent neural network basically does what? It basically works by unfolding in time. And unfolding in time is, when things unfold over time, because the words that I'm speaking, that make, the sequence of the words makes a difference. And we unfold it over the time and do the necessary training. And, when I say I work at South Asian University, so when I work at, so at has to be read in the context I work. So every word has to be read in the context of whatever I've spoken earlier. Whatever have been done earlier, that has to be brought into the context, and that is what is, recurrent neural network. But what was that was, unfolding through time, as I mentioned, that we move a recurrent neural network by unfolding through time, wherein with every word is being fed as input to the network over the time. This is a simple RNN cell forward propagation. I'll not move into the detailed architecture of RNN as of now, because I feel that I would not permit me to take up the architecture part. So this is something like RNN forward propagation, wherein you have multiple cells, and in each cell, input or symbol at a time, or you can say one token at a time. That would be the right word to use. So if I say I work at Salvation University first, then for second cell it would be work, and for third cell hat. So that is how the input goes into each RNN cell, and whatever one RNN cell takes up, it produces one output which is fed as input to the next network cell. But what was the problem with recurrent neural networks? That it had vanishing and exploding gradients. Now, what is vanishing and what is exploding gradient? Vanishing gradient is when your gradients or the derivatives through which we update the weights, they start vanishing. They tend to get zero. When they tend to get zero, what would happen? My weights would not get updated. My weights would not get updated. That means what? The training would not happen. And recurrent neural networks, they had a major disadvantage of vanishing and exploding gradient, wherein if you have a large sentence, per se 50-word sentence, then it would lose out the meaning, lose out the context that was there in the first sentence. So it would start, its memory is short. You can say that, I'll compare it. If you have seen the movie Gajni, there was a short-term memory loss, right? So long-term memory loss and short-term was there. So you can compare it with, that, and it had a vanishing gradient problem. So I have to wind up the session, so let me just quickly go through. Then came the LSTMs, and that were basically developed with the context of long scale memory, long short-term memory. That when I am 20 years back, what I should remember today. So it is based on the concept of there is some short-term memory and there is some long-term memory, and we have to take the long-term memory along. So that was the concept of LSTMs. Then came the encoder-decoder architecture, and encoder-decoder architecture was like, you take a zest out of something and then feed that zest to the decoder. And the transformer, that is what we call the king of architectures, is based on that concept only, wherein if you have studied this paper, attention is all you need. That is based on the major idea was that you parallelize the task that we are doing. In LSTM, we were feeding one at a time. But the revolution that came with attention is all you need paper is, or self-attention concept is, that it parallelized the things that we were doing. And that is the magic that you see today happening when you see ChatGPT or when you see other tools, AI-based tools that you explore in your day-to-day life. So that was your, self-attention model, wherein the major thing is like if I have the, money bank or river bank. So bank is used differently in both, and it has certain context. So it was taking up the contextual embeddings, taking up its position as well. So position and context were taken care, and it was parallelized. So everything parallelized while taking into consideration the position of the things also. So that was the main thing which transformer architecture and the self-attention brought to us. And so, it is really said that GPT-4 is exciting and scary too, because the risks that are coming in with this are immense, and the potential that it has is also immense. So we as individuals really need to explore ourselves, need to upgrade ourselves so that we are relevant to what is happening around us. So I end up with this, that inventing the future is really the best way to predict it. So we have to really, work very, very hard to adapt logical changes that are happening around us. With this, I thank you all. If you have any questions, I'll be happy. Thank you. Yes, any questions from your side? I would be happy to, if any one of you want to explore this and want to get in touch with me. I'm Kavita Khanna from South Asian University. Thank you.
Thank you so much, Kavita ma'am. I would now like to request the Anupam sir to please felicitate Kavita ma'am and thank her for her presentation today.
किसी भी सेशन में मुझे ना वो प्रेजेंट ना स्क्रीन शेयर नहीं कर पा रहे अभी। अच्छा ठीक है, और एक साहिल बाबू करके आता हूँ, वो कोच बना दो। ठीक है ना, किसी भी सेशन शेयर वो नहीं कर पा रहे, स्क्रीन शेयर नहीं कर पा रहे, वो देखने के बाद
कोई नहीं, जैसा होता है
थैंक यू।
Right, our second keynote speaker, Dr. Mohammad Ishwaq from Jeddah International College, Saudi Arabia. We welcome you, sir.
साहिल बाबू distinguished guest and brilliant young researchers here. It's a profound honor to stand before you today at the 7th Doctoral Symposium on Computational Intelligence and third on systems and intelligence. The title of my talk today is Brain, Bots and Smart Grids, a neuromorphic path, ultra efficient edge reality, ready AI. In the next we will embark on a journey that connects neuroscience, electrical engineering, and artificial intelligence. We'll explore how the most energy efficient computer in the known universe, which is our human brain, can inspire us to solve one of the most pressing challenges of our time, making Hello, I'm Dr. Mohammad Ishwaq. I represent Jeddah International College, which is in Saudi Arabia, and I'm here to share my research with you. Before we dive in, let me quickly introduce myself. I did my PhD in computer science, specializing in cybersecurity from Management and Science University, Malaysia. Presently, I'm working with Jeddah International College. Also, I'm also the publication chair for Interactive Conference for Artificial Intelligence in Industries, which is organized by IEEE, Saudi region. My research is mostly in neuromorphic computing, AI-driven security, and smart city technologies. I want to start sincerely thanking the organizers over here, the Institute of Engineering and Technology, Dr. APJ Abdul Kalam Technical University, and the School of Open Learning, University of Delhi, and the University of Calabria, Italy, for this wonderful invitation. It's great to be here, connecting with all of you. Now, I'd like to begin my talk with a quote from Mark Weiser. He's called as the father of ubiquitous computing. He said, the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. Really deep into it, actually. The best technologies these days, what we are looking at it, are once we notice they are ones that work to be seamless. They are not in the picture. They're not in the foreground. They are working in the background, and they have been embedded into the technology so much that it disappears. But we still feel the ambience of it. Talking about, let's look what happens around us. Our energy, since my talk is mostly about energy and neuromorphic computing, that is brain-related computing. So I'm talking more about energy, and specifically I will be talking more about edge-level energy or edge computing. So we see around, we see solar panels popping on the rooftop everywhere, wind farms, every riverbed, electrical vehicles are becoming common on our roads nowadays. And people are no longer just consumer of electricity, but they are also producing this electricity. So there is a new term called, and that is called as prosumers. Producers as well as consumers at the same time. This is exciting, but it also creates huge challenges. The old power grid, which is the conventional power grid, designed for simple one-way flow. Power plant generates electricity, send it to the home, and done. That's it. But today's they are chaotic. Two-way dance of energy. Two-way dance of things. People have become consumers as well as producers of energy. So to handle this complexity, it will not work with a normal or a general grid. We need smart grids in this case. So what is a smart grid? It's a when what happens here in the smart grid that it predicts with future demand, it optimizes itself, and even heals when someone goes wrong with this grids. So at the heart of the smart grid lies a critical capability. We call it as short-term load forecasting. And if any grid is there, then what kind of energy level that need to be consumed by the consumer, that need to be forecasted. And this forecasting is not a very long term, but it is a short term forecasting. And I trying to forecast it a while ago. Maybe it could be an hour, it could be a minute, some minutes, or a day kind of thing. That is why the term short term load forecasting. So we put this short term load forecasting to predict how much electricity we will consume in minutes, hours, or days ahead. Why matter? Because we can predict a heat wave cause everyone to crank up their AC. People, if it's there a heat wave around there, people simply start using their AC, the maximum extent. So it can predict during this specific period where the consumption becomes higher. We can prepare, you can't predict it, there is blackouts. Yeah, people, the grids are not ready for that. The grids are not ready for this heavy load actually. So if we over predict, we waste money activating backup power plant. Forecasting isn't just a academic exercise. It's literally, we call it as the nervous system of our modern grid. How do we been doing this forecasting? That there were a lot of technologies available in the past. This is not the first time we'll be forecasting, but a lot of technologies available in the past which were used for forecasting. Some of them are, like I say, if there is a tool called Arima. They were elegant, easy to understand, and could run on tiny computers. Very sophisticated, actually. But the problem with this tool was it couldn't capture complex pattern in energy use. That's the main problem. Okay, coming to the next thing, that is the machine learning tools like XGBoost or Random Forest. Okay, they have better accuracy, but still need a lot of manual work to create right feature because we will be extracting important features from it. So it will be more manual there. Okay, let us go to the next level. The next level, like what Professor Kavita just explained us about artificial intelligence, specifically the CNN part, the deep learning part, that is convolutional neural network part. Okay, it's good in capturing patterns like LSTM. She just discussed about LSTM, long short-term memory. It masters the sequence over the time, and recently, the very latest one is the transformers. We call it as TFT model. It has achieved incredible accuracy. Now, beginning, we started from ARIMA, we went to machine learning, then we went to deep learning. In deep learning, we go for CNN and transformers, but still we lag something if we come to the power grids. What is that thing? Each step brought us closer to perfect prediction, sound great, right? But here the catch. All these technologies, they are accurate. There is no doubt that they are not accurate. They are accurate, but they come at a massive cost. And what is that cost? These models need powerful GPUs, cloud servers, and huge amount of energy. That's the main catch in this. And that creates a fundamental problem. Okay, how to solve this problem then? So let us try to understand the deployment gap. Okay, I'm not telling that these technology which we just discussed, they are not good in predicting or in the accuracy part. Okay, they are really very good. But when it comes to deployment, they have a small, you can say, thing there. So let me ask you something. Where do we actually need this forecasting? You know, we are into the forecasting thing. Okay, where do we need it? Do we need it in the cloud data center? Yes, of course, we need it for planning. But very importantly, we need it at the edge. Now we are talking about grids, smart grids. Smart grids means technology needs to be over the smart grids. Right? That's the edge actually. So we need it inside the smart meter on your home. We need it in the IoT gateway, controlling the neighborhood microgrid. We need it in the charging station, managing electrical buses. So these are the points where actually we need this deployment of these things. But imagine technologies with huge hardware like GPUs and all, we cannot simply put it over these small devices. It will be really very difficult to deploy it on these devices because they are really not very powerful. They are very small in nature actually. So these are small resource constrained devices. They have limited memory, limited processing power, and most critically, limited energy. So many runs on batteries harvest energy from their environments. That's the problem with this technologies. So that's the problem. Our best model, that is the transformer model or the LSTM model, simply cannot run on these devices because of their hardware constraint. They are too big, too slow, and too power hungry. That's the problem. So how to wipe out this gap? This gap that works in research papers and can actually be deployed in real world. And what can we do? We call it as a deployment gap. So we've been so focused on winning leaderboards, we forgot ultimate goal. And that is, we need to deploy things in the wild. In the wild, in the sense, on the edge, on the grid there. So blind spots of forecasting. See, our main idea is about forecasting of energy consumption here. So where do we actually lag behind blind spots? There are two blind spots here. One is the energy. Second thing is the what really matters. Let me explore this. Coming to the energy, we measure performance in FLOPs, okay, or in MSE. So these are really very fancy terms, but they don't tell us what actual energy consumption is when a device is running 24/7. If it is running 24/7, how much it consumes? That is the main problem with this things. Think of like if you say, for example, if I'm having my car in a garage and I keep it running 24/7, and it's of no use, but still it's consuming the energy, right? That's the incredible wasteful of energy there. Now, second blind spot here is what really matters. We optimize for average error. See, error calculation is the most important factor here. We can say any technique, any implication is good when it gives us less errors. So when it comes to errors, we have certain matrix here like MAPE or RMSE. The problem with this is that they treat every mistake or all the error as equally bad. There is no distinguishing between errors there. So, but they ask, if I simply ask a grid operator, which is standing or sitting over the edge there, is missing a forecast at 3 a.m. on Tuesday is similar to missing at 5 p.m. on a scorching summer Friday? You will say, yes, it is not same, it is completely different. Then why we are trying to calculate the error rate at both these times in the same way? It should not be calculated in a similar way. So, under forecast, peak, and you risk in blackouts, expensive blackouts actually. So, this basically says that all errors are not equal, but our standard loss function treat them as if they are all equal state. So these blind spots have led us to create model that look great on paper, but miss the mark where it actually counts. So this is one of the main reasons that calculating error and trying to put it common in all over it will not be recommendable actually. So these are two blind spots there. Now, okay, what's our inspiration for this technology of neuromorphic technology? So where do we turn for better approach? What is the better approach? For decades, we're looking for silicon chips. We'll be looking into computer architecture like von Neumann. As a computer science students, you know what a von Neumann model, input, processing, and output there. And again, that is not providing us the solution. These chips, silicon chips, of the von Neumann model. But where is the solution? The solution is in your head, and that is your brain, actually. We get our inspiration from our brain, how it works, how it functions. Here is a remarkable fact, actually. The human brain runs on about 20 watts of power, and that's less than a dim light bulb. What we use in our household there. Yes, it can process complex, yet, even after consuming 20 watts of power, it is capable of processing complex information, make decisions, learn, adapt continuously for an entire lifetime. Not for a short period, but for an entire lifetime, actually. So how does it do this? The secret is how it operates. Event-driven. And second thing is asynchronous computation. These are the two important features of a human brain which need to be adapted into a technology. In regular computers, we already know that there is a clock constantly ticking. Even if there is a process happening, the process is not working, but the clock is still ticking. And in the brain, actually, neurons are mostly quiet. Our brain, like what Professor Kavita just explained about neurons. Neurons, on the other hand, in our brain, they're not constantly working. They only work when it needs actually, and most of the time they are quiet. They only fire, only consumes energy when they have something important to communicate. This is called as sparse event-based processing. Only when it needed, not all the time. Not like my car standing in the garage and it's running 24/7 and it's consuming the energy. The technique should be like a brain where it sparks only when it is needed. So the principle here inspired a new computing paradigm, and that is neuromorphic computing. It's a new paradigm actually, and very advanced. Companies like Intel and IBM, they are coming up with these chips actually, which is mimicking human brain. Intel is coming with a chip called low-H chip, and IBM with two knots. These are hardwares they built, Intel and IBM, and they are trying to mimic human brains over these chips actually. So, and the heart of this hardware, there is an algorithm lying. And what is that algorithm? Let us explore that. That algorithm is spiking neural network, SNN. Unlike regular artificial neurons that fire at every step, spiking neurons communicate through discrete ray events. They simply communicate using spikes, fires where it needed. Let me explain you how most common model, so leaky integrated fire neurons work. Let me give you an example of a tiny leaky bucket. Okay, this is a bucket. Each incoming spike adds a drop of water to the bucket. Between spikes, the bucket slowly leaks. It's not a regular bucket, it's a leaky bucket. So each drop of water is actually spiked there. If enough drops arrive quickly enough, the bucket fills up and overflows. That overflow is the neuron firing. When it overflow, when the bucket is overflow, then that's when the neuron fires on its own. This simple mechanism gives SNNs a natural form of memory. In previous techniques, they used to remember from their past. But here, these neurons, they have their own short-term memory. They will create their own short-term memory units. They don't need complex structure like LSTM to remember past information. The memory is built right into the neurons' dynamics. And because the computation only happens when spike occurs, they are perfectly suited for energy efficiency. That's the main reason we are using this technique in energy forecasting or energy efficiency forecasting. This makes them natural fit for time series problems like load forecasting. So when I say about SNN, and it is so advanced, it is so natural, so human-like, then why has it neuromorphic computing already reached as HAI? Why it is not common? Why don't we hear mostly about it? The honest answer is SNNs are really hard to work with. They're very difficult to work with because of certain parameters. What are these? Let me explain you. They come with three major challenges. First challenge is training in instability. We cannot train them. The spike function isn't smooth. It's not really. See, our brain is unpredictable actually. Similarly, if you are trying to adopt the same technology over a chip, then the spiking technique isn't smooth actually. So it's hard threshold. You can't just use standard back propagation there. Even with special technique, we cannot control it. So network can't be unstable in this case. So neurons either fire too much, wasting energy, or they go completely silent, contributing nothing, sleeping for a longer time. That's one challenge. Second challenge is adding context. And how do you tell a spike-based neuron that it's a holiday or it's a peak time, it's 5 p.m. How much energy should be consumed on a holiday or on an evening or on a summer afternoon? So how will you tell the neuron about this? That's the second challenge. Third challenge is the accuracy gaps. Despite the promise, pure SNNs haven't matched the performance of a regular neural network in complex tasks. If I say simply, if you ask me if I compare SNN with my TFT, transformer technology, or CNN, convolutional neural network, I must say CNN, deep learning, transformer technology, they are better in accuracy. Then why we are using this SNN technology? There is a catch in that. I'll explain you that. So by their problem, so the question here led to the work I'm sharing today. We set out a line to build a pure end-to-end trained SNN that could compete with regular neural network while keeping all the efficiency benefit of even computation. Now, we didn't just take an existing SNN. We are trying to compute or trying to take pure SNN or trying to form a pure SNN and apply it to a new problem. We designed a purpose-built architecture, three key innovations. First innovation is spike encoded context. Second is homeostatic regulation. Third is a peak weighted loss functions. All either brain inspired actually. If I talk about spike encoded temporal context, it will help our network understanding time and calendar patterns. Why time and calendar patterns? Because here I'm trying to forecast the consumption of energy on a particular hour, day, or a week, or a month. So this time and calendar need to be synchronized, need to be taught to my SNN. Second thing is homeostatic regulation. Now, In the previous slide, I explained that SNN is really how to make it stable. So we have a natural brain inspired mechanism, and we call it as homeostasis regulation, which keeps the training stable. Third is peak weight loss function, focusing on what really matter, getting the peaks right. What here the peak means the peak consumption of energy, and what will be the loss if I compare the peak weight with my regular consumption. Let me take you through each of them one by one. If I talk about spike encoding temporal context, uh, in forecasting, calendar information is essential, like I said earlier. Power used at 5 p.m. on a Friday is completely different from 3 p.m. on Monday. So regular network just add these as extra input memory. But in SNN, everything must be spike trained. If I talk about CNN, okay, they can train something, some data set, and simply they can get a specific time, specific hour, or specific day. How can I train my SNN here? Okay, because it is spike based. So everything must be spike trained here. So we need an encoding scheme. We have a specialized encoding scheme here to train SNN architectures. And that specialized encoding scheme is rate-based Poisson encoding. What exactly this is, let me take you through that. We take our load data and normalize it between 0 and 1. Then we generate spike randomly. The higher the load, the more spikes will be generated. Higher demand means dense spikes. Low demand means sparse or low spikes. So if we do exactly the same for our calendar features like days or months or weeks, we can say. So hour of the day from 0 to 23. We have 0 to 24 hours. So if we start from 0 and 23 get converted to spike density. On the other hand, days of the week works the same way. For holidays, we generate dense spikes, and for regular days, the spike will be less in number. So all these spike trains, the load history, the calendar info flow together into the network. SNN doesn't need special mechanism to handle these contexts. All arrive at spikes, and the network learns through training how these patterns relate to future demand. If I come to my next innovation, that innovation is biologically inspired homeostasis regulation. As I mentioned, SNN training can be chaotic. Neurons either fire too much or they get too silent. Nature solved this problem millions of years ago through a mechanism called homeostatic plasticity. Here, how it works is in real brain, in a human brain, actually, this is a mechanism which is in our human brain, actually. Every neuron has a target firing rate. If a neuron fires too much, it automatically becomes harder to fire. If it fires too little, it becomes easier to fire. So this keeps the entire system balanced. So that's the main idea of using the second innovation, that is homeostasis regulation. Coming to the third one, that is weak weight loss redefining. The problem with SNN is it can be unstable and it can be runaway excited or new neural silent destabilizing the network. The solution for this is each neuron has a target firing rate. It's threshold adjusts dynamically based on recent activity. So there is an actual rate and there is a targeted rate. So this rate will be stabilized at certain point. Now there is a weight here which has been implied. By adjusting this weight, we can simply stabilize this firing of neurons. This will give us better accuracy. Coming to the architectural overview of this model, look at this figure. You can see this on the left hand is our input layer. it takes 48 hours window of past load data plus calendar features, hour of day, day of week, holiday indicator. Everything is spike encoded using Poisson model, which I described in my previous slide. This input feed into the second hidden layer. So we just have two layers here, two hidden layers here, not multiple hidden layers. So this input will be into two hidden layers. Each with 128 leaky integrate fire neuron. Every neuron in this layer, now consider this leaky neurons as your leaky buckets. When the leaky buckets get overflow, then it starts a spike. It gives a spike. It gives a spike there. So the final layer connects to a single output neuron. This doesn't spike. It simply reads the accumulated activity and produces our prediction for the next hour load. This is actually the output which you got from these two layers here. The whole network is trained end to end using special techniques that let us backpropagate through the spiking dynamics. It is a simple architecture. It is not as complex as what we have just seen in the convolution neural network or transformer networks. Just two layers, but its power comes not from complexity, but from careful design for the specific task. Now, let us come to the experimental setup of this model and the baselines and the comparing our model with the other baselines. We use UK Dell dataset, a public collection of real household electricity data for the UK, United Kingdom. We aggregated the second by second reading to our consumption, creating a realistic forecasting scenario. Now we compared our model against strong baselines, like we discussed earlier, starting from CNN, that neural network, then LSTM, TFT, XGBoost, all are really good in their own field. If I talk about CNN, it is the good in capturing local patterns. If I talk about LSTM, it is perfect in classical approach for sequences. If I talk about TFT, it is a state of art time series for forecasting and gives you better accuracy. XGBoost, on the other hand, is powerful tree-based method. It's still highly competitive. Now, if we evaluate on multiple metrics, we are comparing our model with these standard models. So they have seen certain metrics. What are these metrics? Standard accuracy, like NLP, RMS, and NAE. Peak performances, error during top 5% demand hours, and how they perform during the 5%. Like I said, on a scorching summer afternoon, during holidays, 5 p.m. on a Friday evening. So these are the peak hours actually. So we try to measure them on these peak values. This dual focus on accuracy and efficiency gives us a complete picture of how each model performs. If you look at the results here, the results will be surprising now. The transformer TFT performed best NAT, that is 49.82. RMSC is 0.212. XGBoost is right there with it. Excellent results. Our estimate, our model, achieved MAP of about 52.84%. It's competitive, but it's not the leader in the matrix. If you compare it, we compare it with other models, it's not the best one. Then why we are still using it? Now you might think our model is interesting, but not good enough. But what makes is poor entirely actually. This small increase in average error, about 3% point, is what we call the price vision. If I talk about my previous slide, I mentioned in my first slide, right? As the concern is not the accuracy, the concern is the deployability of the model over the edge. So I'm coming to that actually. It's a cost we are willing to pay for the massive gains. We are about to see the efficiency in what really matters, peak performance. The right question is, which model has the lowest MAP? Which model gives the best combination of accuracy, efficiency, and real world value for edge deployment? And that's this gets interesting. Let's look at this table here, okay, which shows performance during those critical peak period. Now, our concern is not a normal time. Our concern is the peak period. If you can see here, CNN gives me 0.31, LSTM is 0.365, TFT is 0.352, XGBoost is 0.352 peak, and my SNN model is giving me 0.298. That's a 15% improvement over the best baseline and up to 27% over other baselines. That's the catch here, actually. That's the second. Our pure SNN designed for ultra low power hardware is more accurate during the peak than the massive transform running on a GPU. Now, my hardware is simply chip based. The other baseline hardwares are GPU based. They are massive hardwares. My hardware is only a chip here. So, comparatively, I can say that my improvement is 15% better than the best baseline, and overall 24 or 27% as compared to others. This is the direct result of our peak weight loss. The model has learned that getting peak right matters most. Its focus, its limited capacity, where it has biggest impact. Normally, when I say that calculating or forecasting during the normal time, when people are in offices and in households, there is not much power consumption. The use of the forecasting of power consumption is useless there actually. But when it comes to peak point, when it comes to a time when we have scorching heat, when the ACs are on, when we are in the afternoon, when there are thunderstorms. So forecasting during that specific period, during that peak time, is really graceful. Yeah. Now let's talk about efficiency. CNN needs 12.5 million operations per prediction. LST, on the other hand, needs 8.7 billion operations. XGBoost needs something around 0.1 million. Our SNN just needs 58,200 operations. That's now let's translate this to energy. If I talk about it, let me come to the conclusion directly. Here, 4,000 times more efficient than CA. My SNN is 4,000 times more efficient than CNN. I don't want to take you through the mathematics here. Now, if you compare your baseline performance, hour of the day of the week, holiday spike added, dynamic threshold, and all that thing, with peak weight loss, full modern estimate, it's giving 19.4% improvement in peak MAEs. So what does all this mean? It means that the best model is not universal. It depends entirely on where and how you deploy it. That's the main point, because we are trying to deploy our model directly on the edge. We are not sitting in a room, AC room, and trying to predict the forecasting. No, my model will be on the edge there, in a small chip over the edge. If you are running forecast in a cloud data center with unlimited power and computational resources, by all means, need a transformer. See, I'm not trying to demotivate the other technologies. So they have their own places to be adopted. Like say that if it is a cloud data center, normally cloud data center, they have unlimited power supply and they have lots of computation resources. So in that scenario, transformers or XGBoost, they are more accurate. They are well understood and appropriate for that context. If you are deploying an edge with a smart meter or IoT gateway, a microgrid controller, the rule changes here. Because we do not need high-end hardware there. We do not need high power consumptions there. So here, what is more suitable here? Here, the problem is the power is limited. At the edge, the power is limited. Real-time response is critical, and operational reliability during peak is paramount. So, in that context, our SNM is not just an alternative; it's the only viable option that delivers all the low power, real-time capability, and peak-aware accuracy. This leads us to a broader call to action to our research community. We must broaden our evaluation criteria. When we publish a new model, we should ask first thing, what does it cost to run this model in terms of energy? Can I run it on edge hardware? Is it optimized for the event that accurately matters in practice? In another way, the thing is deployability. Is it really deployable? We do research, we do it on a paper, we do simulations, but what about the deployability? We need to think about deployability. As a researcher, you should also think about deployability, not just some theoretical concepts or just simulation kind of things. Accuracy is the leaderboard in one dimension, but the real world efficiency and operations relevance are equally important. We need to redefine what success means in the age of edge AI. That comes to my conclusion. So we have demonstrated pure spiking neural network are not just a theoretical curiosity, they are a viable and strategically advantageous paradigm for edge-based short-term load forecasting. So three key innovations spike in coding context, homeostatic regulation, peak weight loss. We've closed the performance gap with conventional deep learning while retaining full efficiency of event-driven computations. Our model enables a new class of application, always on real-time forecasting on resource-constrained devices, with a focus on peak period that matter most, grid stability and cost. This is a blueprint of transition from centralized, high-power AI to distributed, sustainable, and resilient edge intelligence. It's a step forward, making AI disappear into the fabric of our infrastructure, working silently and efficiently in the background. Now, conclude. I want to express my deepest gratitude to the organizers of Dosci and Comsia for this incredible opportunity to share my work. Thank you to the technical program committee and reviewers and the entire team that made this event possible. I also want to acknowledge my colleague, Dr. Tariq Henry, whose collaboration and insight was essential to this research. And most importantly, thank you, audience, for your time, your attention, your engagement. The question and discussions are open. You can ask me if you have any questions. That's where I actually.
So how does like SNN perform other data as well? Like you specifically did for a short term like STLF, sorry. But like data, medical data like that are similar, like EEG medical data or other kind of data. How like SNN performs?
Unconventionally. Normally, what they do nowadays is simply convert this SNN data to CNNs. That's unconventional. It's like, reinventing the wheel. That should not be done. So it's a work in progress. We have started with the smart grids. Okay. It's work in progress. Yeah. Research is going on. I'm not really happy. It's not there. It's there actually. Research is going on. And very soon it will be, in both of the other fields. Any other questions? Yeah.
पेपर जो दो तरफ से वो आप आ जाने थे
So my second is like anything. More work is specifically for the smart grids. But if we like the use for then about the healthcare thing. So can we not constrain with edge device only for data pre-processing or for cleaning? Because at last the accuracy matters. So can we not analyze that onto the cloud for the application kind of like healthcare kind of thing? So for a smart grid, I think that SNN can work,
But in the case when the application is more like say more senior, then can we rely on SNN?
See, like I said in my presentation as well, the other techniques, like I said, CNN, XGBoost, transformer technology, they are good in accuracy. And even if you see the results of mine, others they have got better results than my SNN techniques. So my deployment is at the edge,
Yeah.
and that is reducing the complex hardware there. Because my SNN will come inside a small chip and that is easily deployed there. That's the main thing here. But it's like comparing apples with oranges.
Certainly, there's nothing kind of
That's, I'm not constrained to energy preserving. No, SNN is in many other areas nowadays. I must say it is still work under progress, but people are. I used it for energy consumption. Other researchers are there who are also trying to use it for other purposes. Thank you so much, guys.
Thank you, Professor Shah, for such an enlightenment talk related to cutting edge technologies, deep learning, machine learning in the area of smart grid and computing. Now, I would like to call Gulshan sir to facilitate Mohammed Ishaq sir. Thank you. Now we will proceed for lunch. After lunch, we have a presentation in the respective sessions. So all the participants, you are requested to check your spectral room corresponding to a session. And we have a idea for here in the seminar room. And apart from that, for the respective sessions, we have room number 217, 219, 301, like these 4 rooms are there. So you can go there. Right? Thank you.
मैंने इसको छेड़ के जाऊँ दोबारा लीव ना हो